Hello everybody and welcome to exercise 8. This is the last exercise on our list of final exam review problems. And in this problem, they're asking us to calculate a derivative and an integral in an applied situation. This is going to be a nice opportunity to kind of tie together two of the main concepts in our course this semester. All right, so let's read this question together. So they tell us at t hours after noon, the electrical power drawn by a household is given by a function f of t. Units of that power are kilowatts. Okay, notice that this function is being given to us in tabular form. We've got a table of data here that's telling us the power being drawn at various times. And remember again that t is representing time after noon, so t equals 0 represents noon. All right, so let's see if we can do part A together. So they'd like us to estimate f prime of 4. Okay, and if you think back to the graphical meaning of the derivative, it's just the slope of the tangent line to a function. Okay, but we don't have a formula for our function, so there's no way to really find this slope exactly in this point. We really have to approximate it. And way back in the course, we talked about something called the central difference approximation. If you want to estimate the slope of the tangent line at a point, you can find some points that are close by, maybe 6 and 2, and just find the slope of the secant line that runs through those 2 points. So we're going to find rise over run, okay, between those 2 points in our table. That's not going to give us the derivative exactly, but it's going to give us a decent approximation of it. All right, so let's see if we can do this calculation. So our table tells us that f of 6 is 0.39, f of 2 is 0.69, 6 minus 2 is 4, and if we do that calculation, we're going to get minus 0.075. Okay, but more importantly, they want us to give an interpretation of our answer in the context of this problem. What does that derivative mean? What does that mean in the context of this problem? Okay, well, to get started answering a question like that, I always like to start with units. Let's think about units here. Okay, so in the numerator, we subtracted 2 output values, and we can see from our table that the units of the outputs are kilowatts. Okay, and then we divided by times, 6 minus 2, and time is being measured in hours. And so looking at those units, we can see that the units that we have here are kilowatts per hour. Okay, and that unit tells us that what we're really talking about here is a rate of change, the rate at which the power being drawn is changing. Okay, so here comes our interpretation. Okay, so we'll start with the fact that t is equal to 4, so that's giving us a time of 4 o'clock p.m. Okay, and we just figured out by looking at our units that the power drawn we can see from that negative value that it's decreasing, is decreasing by about 0.075 kilowatts per hour. Okay, so we've just explained what that derivative means. We're just measuring a rate of power change, basically. All right, and I think we've answered what they wanted us to answer in part A, so let's move on to part B. And part B asks us to estimate the value of an integral. Okay, the integral from 0 to 12 of f of t. Okay, and graphically, an integral is about estimating area. Okay, and one way that we had of estimating area was looking at left and right sums. That's kind of a natural way to approach this given the fact that we're dealing with a table of value. So what would the left sum be? Okay, well, just because of the fact that kind of looking at the number of data points in our table, it's natural to use 6 subdivisions. Okay, so we're taking the interval from 0 to 12 and we're dividing it essentially into 6 equal pieces of width 2. Okay, so if we want to do a left sum, we're interested in the output values at the left-hand endpoint. So our first entry would be 0.73 times the width of the first subinterval. That would be 0 to 2. So we're taking that times 2. Then we'd move on to the second interval. That's from 2 to 4. The left-hand endpoint there is 0.69. That's going to get multiplied by a width of 2. And you probably remember this process. We're going to continue with this, taking left-hand endpoints times widths until we get to the very last interval. Okay, continue this sum down here. 0.38 times 2. And then the very last interval from 10 to 12, its left-hand endpoint would be 0.28. That's going to get multiplied by 2. Okay, and you might remember there's kind of a shortcut, a better way of writing this. Since there's a 2 in every single term here, it's customary to kind of take that 2 and factor it out. So an easier way to write this would have been to write just 2 and then to add up these numbers. Okay, and that's a calculation that we can do. I'll let you confirm the fact that if you do that, you're going to get 5.98. Okay, think of that as that's our left sum approximation of this integral. Okay, but if we want to be accurate or get more accuracy for this integral, we could also calculate the right sum and then maybe take the average to get an overall estimate. Okay, so I'm going to do one more calculation here where we do the right sum. It's going to look almost the same as what we did. We're going to have rectangles of width 2, but this time we're going to focus on the right-hand endpoints, which means that for the first subinterval between 0 and 2, we're going to start this time with the number 0.69. That's on the right hand of that first interval, and then we're going to continue. You can look at the table and confirm these numbers that I'm writing down. Okay, and the very last number is 0.23. That's our very last right-hand endpoint. Okay, and you can do this calculation and confirm that you're going to get 4.98. There's our right sum approximation. Okay, so what would be our best estimate of the integral then? Okay, well, we could just take the average of these two numbers. Okay, that has a tendency to balance out the error in both of those approximations. So our integral is going to be L6 plus R6 over 2. We'll just take those numbers and average them. Okay, and you can confirm that that's going to give us numerically an answer of 5.48. Okay, but again, what about the interpretation? What's the meaning of this? What did we really calculate there? Okay, let's think about units again. So an integral is about area, and so if we go back to our integral and ask what are the units of these two pieces, f of t was being measured in kilowatts, and time was being measured in hours, and so we're going to get the kind of unusual sounding units of kilowatt hours for this answer. Okay, you ever heard that unit used anywhere before? Okay, if you've ever looked at your electric bill, you might have seen kilowatt hours. That's what you actually pay for. And at the beginning of the problem, they mentioned, let's just scroll up and see if we can find it, energy usage is actually measured in units of kilowatt hours. Okay, and that gives us a way of explaining this calculation that we just did. Okay, so what we have just estimated is energy usage over a 12-hour period of time. That's what the limits of integration are telling us. So let's try for a sentence here. Okay, so this means that between t equals 0 and 12, which would be between noon and midnight, okay, the household uses about 5.48 kilowatt hours of energy. Okay, and there's our interpretation to explain our answer.